many of you already know very well. Dominic Bruzzese is senior, completing the BS/MS program in Material Science and Engineering here at Drexel. I'm not sure exactly when Dominic formally joined my group, but it was pretty early on. I would probably say sometime during your second year. I've had the privilege of having Dominic in several of my own lecture courses, and he has been involved in all sorts of ways in the lab. A couple of co-op experiences, one at Micron Technologies, other in structured materials, probably opposite ends of the spectrum in terms of scale of industry. And this project was evolved out of an STTR grant we have from the Army Research Office. And in any case, without further ado, Don.
Thanks. Hi, everybody. Okay, so thank you for the introduction. It's good to hear all this. Okay, I'm going to talk today about the use of my project, the use of vase in determining composition and thickness in VST thin films. Significant advances have been made in the understanding of ferroelectrics, and so it was first discovered in 1920. Recently, the effect of compositionally grading these ferroelectrics has resulted in improved properties. And now there's growing interest in studying these materials as electric field tunable dielectrics. The basic operating principle of an electric field tunable dielectric is seen in its capacitance versus voltage character. So there's a strong electric field dependence of the dielectric permittivity. So by applying a bias, you can control the capacitance of these materials. Tunability was defined by Dr. Bond and Dr. Alpe as the difference between the maximum and minimum capacitance values divided by the minimum. And you can see here, this is some data that I took with Eric Gallo, my grad mentor. The bottom curve is a single composition ferroelectric film that gave a tunability of about 30%. But the top one is a compositionally graded thin film, so it has 3 different compositions. And you can see a big increase in tunability as well as capacitance overall. So this is one of the reasons we're looking at these. Also, because of this behavior, you have now a tunable frequency response. So you can control the speed at which an electromagnetic wave propagates through the material. Or in other words, by applying a DC bias to your material, you can control the RC time constant of the device and introduce phase delays. And so we can make some interesting devices with that. In particular, graded ferroelectrics can do this at high frequency, even with low losses. So that makes them an important competitor to semiconductors and MEMS devices, which would also be used in these. So if we can do this with these thin films, then we can make some useful devices. For one, we can make varactors, which are electric field dependent capacitors. They're commonly used in the voltage control oscillators. And tunable phase shifters, like microwave frequency phased array antennas, which supersede mechanically steered radar in their technology by having an electronically steered beam. So a good candidate material, which fits all of these properties, is barium-strontium titanate. Barium-strontium titanate, or BST, is a solid solution of barium titanate and strontium titanate. It packs itself in the cubic or in the perovskite structure. There's a central titanium ion surrounded by an oxygen octahedron, and then at the corners are barium or strontium. So depending on your alloy percent, if you have 60% barium, 40% strontium in your BST alloy, then 60% of those at the corners will be barium ions, and 40% of them will be strontium. Barium titanate is known for its high dielectric constant, as well as it being ferroelectric up to 100 degrees C. Strontium titanate is paraelectric, and like barium titanate, is known for its electric field tunability. It has a strong electric field tunability. So by alloying them together, one gains control over the Curie temperature of the alloy as well as the tunability. And then again, we can use this and make a compositionally graded multilayer structure, get these properties that we're talking about. BST thin films can be synthesized by a lot of different techniques, but the two that are important for this work, the two that are important to understand for this work are metal organic solution deposition and metal organic chemical vapor deposition. The films produced in the study were made by the MOSD technique and are made by the dissolution of 3 metallic precursors, barium acetate, strontium acetate, and titanium isopropoxide. They're dissolved in their respective solvents and then combined in the desired stoichiometric ratio. The solution is then spin-coated onto a substrate. The substrate rotates at about 3 to 4,000 RPM, and then subsequently is heated to 300 degrees C to remove any organic addenda. The spin coat and pyrolyze step is then iterated as many times as is needed to get the desired thickness of your film. Finally, once you have the desired thickness, it's annealed in ambient oxygen, anywhere from 600 to 800 degrees C. Now, MOCVD is the scale-up method of choice for these films. It works by metallic precursors in the vapor phase are pushed by an inert gas, and they're controlled by a computer, an input controller, by mass flow controllers, and the vapor is introduced into the high vacuum reaction chamber. The reactants, they react, and they condense onto the substrate. And an advantage to using this is that the films grow epitaxially, so there's no need for subsequent annealing because the films are already crystalline. And again, MOCVD is an industry standard technique, and so it would be the scale-up method of choice. But as you would expect, there can be problems during processing. Some typical problems with these techniques are film roughness, interdiffusion during annealing, and thickness non-uniformities. It's inherent with the processing, but we want to understand them and characterize them so that we can ensure high yield and good quality devices. Also, I wanted to mention that the films used in this study were produced by the MOSD technique on 2 different substrates, or on one of 2 different substrates. One is silicon and one is platinized silicon. Typically, if you had some films and you wanted to characterize them, you want to learn something about them, maybe you would do X-ray diffraction to learn about phase and crystallinity, or maybe you do Rutherford backscattering to learn about composition of the different layers, or perhaps Auger electron spectroscopy if you want to get an idea of the different thicknesses of the different layers. And also you could use atomic force microscopy to investigate topographic roughness. All these are great and they work wonderfully, but it's impractical to use these techniques on a large scale, large volume production films. So what we would like is one characterization technique that performs it's an accessible, rapid, all-in-one characterization tool that can ensure high quality and yield during production of these films by investigating issues like composition and thickness. So the aim of this work then is to develop a framework to use variable angle spectroscopic ellipsometry, or VASE, as this technique which will provide this all-in-one characterization for these films. And the way that I go about doing that is first by developing an unambiguous method or set of steps to determine composition and thickness from these films. And first, to do that, I'll need to characterize VST monolithic samples with scanning electron microscope, atomic force microscopy, VASE, Raman spectroscopy, X-ray diffraction, and FIB and TEM. And finally, I'm going to analyze the multi-layer graded structure and propose a model for its characterization. Okay, so you're all wondering what's VASE. Variable angle spectroscopic ellipsometry is the technique used here. It's an optical technique where linearly polarized light is incident onto a sample at an oblique angle. The light is then reflected, and its polarization state is detected by the ellipsometer. The way the ellipsometer detects the polarization state is with a rotating polarizer, and behind that is a CCD detector. So the ellipsometer actually reads out an alternating voltage. So there's an AC character and a DC offset, and the polarizer rotates at a known angular frequency. So from that information, the ellipsometer can give you psi and delta, which are the ellipsometric parameters. Psi is the ratio of the magnitudes of the electric and magnetic components of the light, and delta is the phase difference between the electric and magnetic component. So through Snell's law and Fresnel equations, we can relate psi and delta to optical constants like index of refraction, extinction coefficient, And then from then we can extrapolate band gap and determine the barium to strontium ratio if it's in the perovskite phase. So here's some raw data from VASE. And so with VASE, we need a computer model to actually extract useful information about a sample. There are some things you can learn from looking at just the raw data. For one, if you look at the delta data, you can get an idea of the thickness of the film by looking at the number of oscillations, but that's only qualitative. Two things I want to point out: that the scales are not an absolute value, because I've just offset the plots to show them all on one thing. Also, the discontinuities you see in delta are due to, again, delta is the phase difference between the electric and magnetic component. Where the phase has reached 360 degrees, it just wraps back around to 0 again to show all on the plot. That's all that is. Again, computer modeling is really key to getting these parameters out of these films after using the VASE technique. So one of the most important parts is creating a representation of the physical system in this model. And there's a few rules with the model. For one, the model must be constructed of layers of different material. And what's meant by that is, physical regions of the film are going to be represented in the model as a block of a certain thickness with a certain set of optical constants. Another rule is that those layers must have parallel surfaces. This is because all of the calculations are based off of Snell's law and Fresnel equations, and one of the fundamental assumptions with those is that you're dealing with parallel interfaces. So that's important. And again, for each of these different layers, thickness and optical constants are going to be the variables that you give to your model. So just to give you an idea, this is a cross-sectional TEM image of a graded VST thin film. And you can see, maybe not so well here, but 3 distinct layers where there's different composition, and those will be represented by the model here. This is just a schematic of the modeling process. So modeling starts off with measurement of psi and delta with the ellipsometer. Then we construct that model in the computer program and give it initial guesses for the thickness and optical constants of the different layers. The model then calculates psi and delta based on what you've given it, and the fitting process goes by the use of a mean squared error reducing function. This program uses the global Levenberg-Marquardt algorithm, and the fitting works by comparing the experimentally determined psi and delta to the calculated psi and delta, and the function basically minimizes the difference between the two by changing whichever free parameters you've set in the model. So the result is an optimized thickness for the different layers and optimized optical constants. And you can use that result as a better initial guess for your model and iterate the process to continually reduce your mean squared error. Again, the mean squared error, or MSE, is a quantitative indication of the quality of your fit. So, and a mean squared error of 0 would be a perfect fit. Okay. So with computer modeling, the fewer variables you have, the better. So we use parametrizations to model the optical constants of these films. One common one that is used is the Lorentz oscillator. It's based on the solution to the differential equation of a simple harmonic oscillator. There's 3 fitting parameters: the amplitude of the oscillator, the center energy of the oscillator, which is where it's located, and the broadening term, C. The top Lorentz model is built off of the Lorentz oscillator model, and it's better. It's a piecewise function which forces the extinction coefficient to be 0 at energies below the band gap. And so the result in using the top Lorentz is an improved model fit. So that's the one that we use for the model. This is a representation of the parametrization. This is what it looks like. And the main difference that I want to point out is how quickly the Lorentz goes to 0. This is the dotted line is the extinction coefficient versus the top Lorentz. And then again, the result is an increased, a better fit in the model. So we want to get the fundamental band gap using the parametrizations, because the fundamental band gap, we know from theory, and Panda et al. Have confirmed that there is a dependency of the band gap on barium concentration. So if we can identify the fundamental band gap of the sample, then we can identify a concentration. However, I just want to point out that the fundamental band gap is going to be what is the indicator, but due to the presence of defect states, the model can kind of be thrown off, and sometimes the model band gap isn't quite the fundamental band gap, and so we have to understand what causes these defect states, and well, we need to understand that. So, for example, one thing that can affect this is varying annealing temperatures. So if you have two different films that were annealed at two different temperatures, they will have different band gaps. And we need to understand these dependencies so that we can take them into account when we're modeling. Okay, so we know now that we need a computer model to use the vase technique to understand, to learn about our samples. So the first step, though, is to characterize the samples to be able to build this model. I started off with my substrates. So for the silicon, is best modeled as simply a 2 nanometer layer of silicon dioxide on top of silicon. And the platinized silicon substrate is actually a little different. So the film is 120 nanometers of platinum on top of titanium dioxide, on top of silicon dioxide and silicon. And as ellipsometry is an optical technique, the skin depth of platinum in that frequency range is only 30 nanometers. So the result is the ellipsometer can't see past the platinum layer. So the substrate in this case is just modeled as a semi-infinite platinum layer. I performed scanning electron microscopy on my samples, looking at the cross-section to get an idea of the thickness of the films, to provide an initial guess to the model, help develop it. It's really not the best way to measure thickness. The variation is about plus or minus 5%. So it wouldn't be used to accurately determine thickness, but it's sufficient to provide an initial guess to the model. So that's what it's used for. Atomic force microscopy was also used to understand the topographical roughness. But the results of modeling seem to indicate that the inclusion of a roughness layer in the model wasn't necessary. There were some cases where the mean squared error wouldn't reduce sufficiently, and in those cases, adding a roughness layer helped, and that would indicate that the film was particularly rough. So the bulk of this research has gone into the development of this method to go from an unknown sample to information about it. So I could give a substrate or a sample to Keith, for example, and I could give him the list of steps, and he could find out what the thickness and composition is. And that's difficult with modeling because sometimes modeling can be subjective. Data acquisition is the first step. So we acquire the data with the vase, and then we'll start to build our model. So depending on the substrate, is it platinum or is it on silicon? And then on top of that model, we'll put, on top of the substrate, we'll put a Cauchy layer. A Cauchy layer is simply another parametrization like the Lorentz oscillator. But it's a phenomenological model that fits the index of refraction well in the transparent region of the spectrum. So for this, my data set is from 250 nanometers to 1,000 nanometers, and I've restricted the range to 600 to 1,000 because that's where the material is transparent, and fitting then the index of refraction. Based on my work, I've come up with these optimum starting parameters, and then for the thickness, the best way to start with is you start with 100 nanometers and slowly increase the thickness in the model until the calculated delta roughly lines up with the experimental delta. And then from there you can run the model and get a best fit. Then I found that a way to further improve the fit is to convert the Cauchy layer, which is again a parametrization of the optical functions, convert it to a simple graded layer. And what that simply means is that the index of refraction is going to vary as a stepwise function across the thickness of the film. So you can define the number of steps. I found that 7 works the best, and makes sense when you consider that these films are produced by the MOSD technique. And so they would have 5 to 7 spin coat pyrrolization, spin coat pyrolyzed steps. So it's a possible explanation. But again, the result is an improved fit. This also introduced a new fitting parameter, which is percent index variation, and that describes the variation of the index across this thickness. So now that we've done this Cauchy analysis, we know with confidence the thickness of the film, and we have an initial guess for the optical parameters in a certain spectrum of the data. So now we want to extend the range because we want to model the band gap, and the band gap is around 350 nanometers. It's not in that transparent region. So to extend the range of the model, we'll start by doing a point-by-point fit from long wavelength to short wavelength. And this gives us a tabular index of refraction N and K. Although, as a caution, it's not physically reasonable, these optical constants. The purpose then of them is to provide an initial guess to the Tau-Lorentz parameterization. So I mentioned before the Tau-Lorentz is the way that we're going to model the band gap. So this tabular N and K serves as an initial guess to start off the Tau-Lorentz model. So we fit the free parameters of the Tau-Lorentz model to that spectrum, and then make a graded Tau-Lorentz layer on top of your substrate and run the optimization. So then the result would be optimized optical constants. And now to get composition, we'll take the extinction coefficient, K, and use it to construct a Tau plot. Tau plot goes by first calculating the absorption coefficient, alpha, as 4 pi times the extinction coefficient over wavelength. And then you plot the you plot alpha times energy squared, as this graph on the bottom shows you, as a function of energy. And then extrapolate the linear region of the curve. Now where that line there crosses the x-axis corresponds to band gap energy. So again, this is the Tau plot, and this is how we extrapolate the band gap based on the optical constants. These are some results that were recently published on this work. Again, to this point, we've only been talking about characterizing single layer films. And so this first figure here shows the optical constants, the index of refraction and extinction coefficient of 3 different compositions, 3 different single layers. And this is the model that I used. And then on the right side is the Tau plot for those same samples. And you can see, again, the extrapolation to the x-axis. And the inset there shows the dependence of the band gap on the barium concentration. And if you remember from before, this is similar to what Panda et al. Found. Okay, so now we're going to talk about, the next step in my analysis was to characterize the graded BST structure and to propose a model for, or to propose a physical model for its model. So to do this, we used the photosynthetic ion beam to prepare a cross-section of the thin films. So this is maybe kind of hard to see, but I'll do my best to explain it. This is a front view, and then this is a side view. So basically, if this is the thin film, we've cut into it and pulled out a cross-section. So the BST thin film is right here, and then below is the silicon substrate, and that's a side view. Nominally, the thickness is about 70 nanometers. So then we zoomed in on this red box here with the TEM, and this is what we found. So I'll explain the layers. From the top is a low-density platinum layer on top of carbon, which will just serve as protection for the ion milling. And then the film starts. So you can see 3 distinct layers of different compositions of BST. And then the black at the bottom is platinum. Okay, so also notice that the interfaces seem to be pretty rough, and there's white spots in there too. So from analyzing that, I came up with this following model, which you can see is a lot more complicated. So when you have roughness in a film, you'll model that. Again, you have to have parallel interfaces. You model that as 50%, a mix of 50% void and 50% of the material that is the roughness. So that's the top layer. The interfaces will be 1/3 of the top composition material, 1/3 of the bottom composition, and 1/3 void in the middle. One thing I want to point out too is the annealing procedure is crucial with these films. So the interdiffusion coefficient of amorphous BST of one composition into another is so high that if you made 3 different compositions from your spin coating process and then had one anneal, you would have, in the end, one homogeneous composition for your film. So that requires a multi-stage annealing procedure. So after the first composition is deposited, it must be annealed, and then the second composition is deposited, and then another anneal. So despite this film having been made by that multi-anneal procedure, you can still see this roughness and voids in the middle there. Okay, so in conclusion, I have attempted to develop a framework where Vase and computer modeling can be used as an all-in-one characterization technique for thickness and composition of BST thin films. I've done that by first fully characterizing the BST monolithic samples with scanning electron microscopy, carbon force microscopy, and all the others. I've also then, from that information, developed a model and a method, which is step-by-step for determining composition and thickness, and then I also proposed a graded multi-layer model. So we're aware that error is introduced from the extrapolation of the bandgap using the top plot, and also from the non-zero mean squared error. As a result, we're not yet sure of the composition resolution that this technique is capable of, and also there hasn't been a sufficient sample set to test statistical variation. So for future work, it would be great to address this composition resolution analysis, maybe to have some more samples to, again, get some statistical variation, and then to address the known sources of error. Also, it would be interesting to apply this technique to other classes of materials. It would work just as well for them. And possibly by developing this technique in those systems, we might learn more about the use of Vase as an all-in-one characterization tool and improve this model as well. And finally, this would see the most use and the most benefit if it was developed as an in-situ process monitoring tool to be work in tandem with an MOCVD system to monitor thickness and composition as the films are being grown. Okay, with that, I would like to thank a lot of people. First off, my committee members, Dr. Jonathan Spanger, for always answering my questions and being available too. I have a lot of questions. And if he answers 25% of my questions, that's good because I ask 1,000 questions. So I'm still good. Dr. Schauer, because thank you for letting me use your oximeter, which my whole thesis was based off of. And Dr. May, I'm able to just walk in your office and ask you any time of the day, any question. And it's just really comforting to know that I have this support. Also, Eric Gallo and Keith Fonstock. Thank you for, again, same thing, the questions apply to you. I know at like 6:30 or 7 o'clock he's ready to go home, and I'm like, hey, can I ask you one more question? And Keith, I've always been able to bounce ideas off of you with the oximeter, and again, for training me on it. I want to thank Claire Weiss and Dr. Mirape at UConn for producing the MOST films, and Dr. Melanie Cole and Dr. Mark Ulrich of the Army Research Office. They've supported this research, and Dr. Nick Bracken at SMI, who did some work with MOCVD, produced films with them. And finally, I'd like to also thank the Laser Materials Lab. Everybody has helped me in one way or another, and I'm sure I've left somebody out. But Stephen Ottoman, Stephanie Johnson, Juan Chen, Christopher Hawley, Brian Beatty, Andrew Aklashev, Oren, Terrence, Jenny, Joan, everybody there. Everybody's helped me either with a characterization technique or just to help me understand something. And also, thanks to my family for raising me and giving me the amazing sense of humor that I have. And Jess, thanks for being my supporting person. And she also keeps me sane. She printed out everything this morning. Okay, I'll stop talking. Thanks. Okay, so I know you guys are all burning to ask me questions.
Steve's chair.
Sure. All right, so at this point, we'll take questions from the general audience, and then we'll ask people to leave, and it'll just be the committee and Dominic. So let's start in the back, Martin.
Does scattering from roughness layers matter, or just?
That's a good question. So as long as the roughness is on less than 1/10 of a wavelength of light that's probing it, then no, it doesn't matter. If it is greater than or on that order, then yes, you have to worry about scattering, and then in that case, phase might not be a good technique for me to have a pretty smooth film.
Hey, I just have one question. What did you say?
All right, let me go back to the Yes?
So you talked about the error introduced that due to the several steps and things, but you weren't really able to test the same composition film against itself. Were you able to look at the same measurement on the same film and
Yes.
see what the variation was?
Yes, and it works. So the ellipsometer spot size is about, I use the focusing optic, so it's about 1/2 millimeter by 1/2 millimeter. And invariably, when you put a new sample on, it's going to be in a different spot. And the result is that the model still converges. You might get a slightly different thickness because over a longer length scale, kind of with Oren's question, over a longer length scale, there are film thickness variations. And it works. Does that answer your question? Okay.
Yeah.
You addressed the issue with diffusion between the layers,
Mhm.
and you said that, even if it's a multi-step annealing, you still, when you have the second layer, you also anneal the first with it, right?
Right.
You still have some trouble with diffusion. So my question is, in the end, when you then analyze it, when you did the TM cut, the FIB cut, is there a risk that with the FIB you introduce enough heat to again induce diffusion? So the question is, what do you in the end really see? Is that what you really tested? Or is that what was induced in the FIB?
Yeah, and that is certainly a concern when you're doing those, preparing the samples with the FIB. I know Wanan Chen took his time. He took, it was he and I down in the FIB. Actually, he should take most of the credit for this. But when you use a low enough acceleration or a low enough beam current, you reduce that effect, and so invariably it's there. And I guess.
I think that's probably, yeah.
I mean, I think also ion milling of the sample would help that too, to remove any amorphous layers. But as for, it's sparking diffusion, I suppose that's a possibility. Yeah.
Fine. Just want you to know.
When you had those graded layers, one of the layers had 33% porosity. How did you determine that there was porosity in those layers? Because I would assume that you said you did spin coating, so I would assume that top layer would have went into the roughness of that previous layer, so it would have been 67% top layer and 33, rather than having that 1/3 porosity.
Yeah. The reason that I came to that conclusion was just because of so TEM is a tunneling technique. And so light areas correspond to area where there's a lot of electrons are able to get through. And so I attributed that to voids in there. You're right, with the MOSD technique, you would expect it to wet the surface,
right,
however rough it is. But there are solvents in there, and also these are oxide films. Well, okay, that's not actually part of it. Yeah, honestly, to test, to really give you a good answer, the best way would be to throw that model on the ellipsometer and run it and see how it goes. Because it might turn out that no, it's not voids. It could be.
Is there something you can do maybe with AFM and see if, when you do the topography, see if there's like a crevice or something like that?
Is doing AFM on this cross section. That would be not an easy task. But that would certainly give you some information about it. Because remember that the scale is about 200 or 300 nanometers
Right.
So,
Any other questions?
everybody understand that?
All right, well then, if not, let's thank Dominic. At this point, we ask everyone else to leave, and just maybe we'll ask